So this brings me to another term that's completely related to what I've just been talking about, free energy, or it's often commonly called Gibbs free energy. Okay, and the symbol for Gibbs free energy, let me see if I can write on this. No. Sorry, hold on. The symbol, whoa. Okay, I give up. The symbol for Gibbs free energy is G. So when a reaction occurs, there's always a change in the amount of free energy available. And we can calculate the amount of free energy that we have after the reaction and compare that to what we had before and calculate the change in Gibbs free energy. And this is referred to as delta G. Now, delta G, it's a physics term. We're not going to work with it specifically. I'm not going to have you calculate delta G. I do want you to understand, though, what free energy is and what it means when it increases or when it decreases. So free energy is the amount of usable energy available to the system. So let's say your cell is doing a reaction, any old reaction. If that reaction results in more free energy in the form of ATP being available to your cell, then we would say there was an increase in free energy. If your cell is doing a reaction that uses up energy, then your cell will have lost free energy. And we would say there is a decrease in free energy. We'd say there's a decrease in the amount of usable energy available to the cell. So in relation to changes in free energy, reactions can also be classified based on how their free energy changes. And so those two reaction classifications are endergonic and exergonic. Ender means within. It comes from endo, which also means within. And exer comes from the prefix exo, which means outside of. So endergonic reactions are reactions that absorb energy. So these are reactions, if they're absorbing energy into them, are putting energy into the system. They are sort of holding on to energy. They're using it up. So we would have, since they're using up some energy, we would have a decrease in Gibbs free energy. So what type of reaction do you think would represent endergonic? Would it be anabolic, which are building up reactions, or catabolic reactions, which are those tearing down reactions? Remember that energy is stored in chemical bonds. If you want to put bonds together, you're going to have to put energy into that system. If you're breaking chemical bonds, you're going to be releasing energy. So in this case, if this is a reaction that is absorbing energy, it requires energy. Is that going to be an anabolic reaction or a catabolic reaction? Well, if you said anabolic, you were right. Anabolic reactions require energy because you're building larger molecules up, so they absorb energy. Therefore, we would see a decrease in Gibbs free energy. Exergonic reactions are just the opposite. They release energy. So if they're releasing energy, we would see in that system or in that cell an increase in Gibbs free energy. And as you guessed it, I'm sure, this is what we see in the catabolic reaction. So when we take large molecules and we break them down, we release that stored potential energy inside the bonds of that molecule. And that energy is used to make ATP, so the amount of free energy available in the cell will increase. And so we call these exergonic reactions. Now, we're going to practice in class how to draw these graphs like you see here, these diagrams. These are called potential energy diagrams, or PE diagrams, I like to call them. PE does not stand for phys ed. These are potential energy diagrams, and what they show is the change in potential energy in a system when a chemical reaction is happening. So remember, potential energy is the energy stored in chemical bonds. So the first graph shows you the endergonic reactions right here. Endergonic. And we start at the bottom. The y-axis is the potential energy of the molecules involved in the reaction, and the x-axis is the progress of the reaction, or time, if you like. So we start at the beginning of the reaction, and as it proceeds, we start out with our molecules have about this much energy. The reaction happens. It has to reach a certain point in order to happen. The molecules are being strained. There's a stress put on the bonds in the molecules. You're trying to break those bonds and rearrange the atoms and create new products. And your cell puts a lot of energy into the reaction. And when it's all said and done, we have our products over here. And what you notice is that the products have a lot more energy than the reactants had. And so that tells us that there's energy that gets stored in those products. The difference right here, you see this arrow, the difference from the start to the bottom, or sorry, the start of the reaction to the end of the reaction is our delta G. Okay, that difference. Over here you'll see a term, this is a new term for you, activation energy. Activation energy is the amount of energy needed to start the reaction. It's kind of like pushing a bike. You got to give it a push to get it going, get it started. Once it's going, it'll go by itself for a while. Chemical reactions are like that. They need a push. They need a certain amount of energy put into them in order to strain the bonds to make the reaction happen, and that's called activation energy. Okay, I want to now focus your attention on the exergonic reaction over here. Exergonic reactions, if you notice, the reactants are way up here in terms of energy. And at the end, the products are way down here. So we have a net release of energy. Here's our delta G. And it actually would be a negative number, whereas in the endergonic, we'd have a positive delta G. So when energy is released, it's a negative delta G. So this is exergonic. Energy would be released to the system. So now just take a look at the bottom down here. We have a reaction. If you take glucose and fructose and you put it together, you will do a condensation reaction and produce sucrose and water. So remember that from our look at biochemistry. This is a reaction, it's anabolic. We are putting two smaller molecules together to make one big molecule. So this is going to require energy input. So this is endergonic. We have to put energy into it. And this would be an anabolic reaction. And then over here, here's a reaction where we have oxygen and glucose being combined, and the products are carbon dioxide and water. And I hope that reaction looks familiar to people, because it's a life-sustaining, very important reaction in our cells. This is cellular respiration, where we take glucose and get the energy out of it. And there's a lot of energy released. So this is happening in all your cells right now in your mitochondria, and this would be a catabolic reaction. So these are PE diagrams for both endergonic and exergonic reactions. I would like you to know what the words endergonic and exergonic mean in terms of them as a concept. And I'd like you to be able to sketch a PE diagram for each of these. There's some new terminology here for you to learn, so things like activation energy and delta G, exergonic, endergonic, anabolic, catabolic. There's quite a lot of vocabulary in this section of the course. It's a little bit heavy, I know. Don't panic. You will learn it, and we will be moving into new stuff soon, and we will use these terms. We'll talk about this, and so I think a lot of it will start to come together when you see it in some new concepts later on. All right, so the last thing for me to talk about is just to refresh your memory about what ATP is. We studied ATP when we looked at nucleic acids. It's often called the energy currency of the cell. So this entire tutorial has been about energy and how energy changes in cells, and it all involves ATP. So when we have energy available in the cell, when an exergonic reaction has happened and there's been the release of some energy that can be used, it is stored in this molecule ATP. So if you recall, ATP is a ribose sugar with an adenine group and the 3 phosphates. The bonds between the phosphates are where that energy gets stored. Now, when you need energy, when you're doing cellular work and you're synthesizing chemicals, you're doing endergonic reactions, you need to put energy into those reactions. We simply, our cells, break off a phosphate, and when we do that, we release the energy that was stored in those phosphate bonds. And we produce the molecule ADP, which is adenosine diphosphate. So we can't forget about ATP and ADP. These are the molecules that we are storing all that free energy in and then releasing that free energy when we need it in order to do all those endergonic and exergonic reactions, or anabolic and catabolic reactions. So that's the end of this first video on energy concepts. The next video I'll be making for you in a few days is all about the different kinds of reaction types that happen in our cells. They will involve energy. I will be again referring to them as anabolic or catabolic reactions. Some of them we've already studied, like condensation reactions and hydrolysis reactions. But I will be introducing you to some other important reactions involved in metabolism, in metabolic reactions. So that's all for now.